Hey YouTube, in this video we'll be writing a Python program to solve any position in tic-tac-toe. We'll be doing this by building a full minimax tree under the given position and then solving upwards. So this video does assume that you understand minimax. If you're not sure what it is or how it works, I'll link to a quick video in the description so you can check it out. Tic-tac-toe is a very simple game, but not every position has an obvious and immediate evaluation. So for example, if you look at the two positions on your screen right now, they're completely different, but they both have one thing in common, and that is that X is winning. So this is a little bit more obvious on the left-hand side, where it's O to move, and X has generated two separate 3-in-a-row threats, and obviously O can't stop both of them. And on the right-hand side, the position looks a little bit more innocent because both players have only gone once, but in fact it's completely hopeless for O already. X has a forced win in this position. So you can experiment with this position to prove to yourself that it's winning for X, but the point of this video is to write a program to do that for us, so we don't have to. So this is basically what the top of the tree looks like. You start with the empty position, and then you can place your X in one of 9 positions. X goes first. But it is important to point out that there's really only 3 branches here and not 9, because you can go in the middle, you can go in an edge, or you can go in a corner. And any corner is the same, any edge is the same. It's not like the position is actually any different. So we could drastically improve the performance of our program by checking for symmetries before branching, but we're actually not going to do this. We want to keep it as simple as possible, and we want to generate the full tree, even if it means doing extra work. Because tic-tac-toe is such a simple problem that we don't need to add extra code to cut corners. We just want to show how minimax works. And what's even nicer is the branching complexity actually decreases with each layer. So if we check out, let's say we pick the first branch, where X goes in the corner, now O only has 8 places to go instead of 9. Because X has taken one of those places. And with each branch further down from there, then would only go to 7, then 6, then 5, as the number of spaces left decreases by 1. So it only gets simpler. And this continues down the tree, essentially right up until you reach an end node. And there are really only 3 different ways that the game can end. The first example here on the left-hand side is with X winning. So obviously this evaluates directly as X winning, and it's the end of the branch. You don't need to explore what could happen in those other 2 spaces, because the branch just ends. Same thing with the middle case, except it's O winning, and you don't need to explore those 3 spaces. So the only areas of the tree where it actually goes to completion, where it goes through all 9 layers, is where all of the spaces get filled up. And in this case, that third position is a draw. Alright, so now I'll step through the code. The whole program is pretty much in one file, although I do have a separate file, positions.py, which is basically just a bunch of test positions to test the program with. But pretty much everything is in main.py. The only import is for copy, just because we're going to be doing some deep copying on the position objects, just so we can generate them and modify them throughout the tree. So the way the positions will be set up is just a 3x3 list, where an X is an X and O is an O, and we represent the blanks with an underscore. And here I just have the evaluations hard-coded with X wins, O wins, or draw. So this is what the user is going to see. And then here we have some helper functions. So the first of which is just a function telling me whose turn it is to move. It'll return a Boolean, true for is X turn, false for if it's O's turn. And it's really simple. It just takes the position and counts up how many X's are there, how many O's are there. And if it's the same number, then it's X's turn because X goes first, and otherwise it's O's turn. So that's pretty simple. The next helper function is this isFull function, and all it's doing is seeing if there are any spaces left in the position. If there are no spaces left, that means the position is full, so it'll return true. And if there are any blanks, it'll return false. So that's also pretty simple. The next helper function is getBranches. This one will take in a position and whatever turn it is, and it will return a list of all of the positions that could result from that player making a move. So for example, if we were to pass in the opening position in tic-tac-toe, we would get 9 back with each of those spots for X. And basically all it does is it goes through and it checks to see if it's a blank, and if it is, then it will insert that symbol for whoever's turn it is, if it's an X or an O, into that position, and it'll use a copy of it so we're not modifying a reference to the same object, and then it will add that to the list, and then we return this branches at the end. So however many happen to be in here, it could be 1, it could be 9, however many branches are will get returned at the end. And then we have one final helper function before we get to the main function, and that is for static eval. This will check basically, is either side winning directly in this position? It doesn't do any branching, it just checks to see, is there a 3 in a row on the board right now? And all it does is it basically compiles all the trios that could be a 3 in a row, so the rows, columns, and diagonals. So basically here, we're just turning each row into a set. It makes it a little easier for it to be a set because if it is all the same symbol, it'll just be 1 because sets don't contain duplicates. So this is very direct. We check all the columns, basically the kth or whatever, the 0, 1, or 2 index of each column. We add a trio, and then we do the diagonals. So this is just I, so this would be 0, 0, 1, 1, 2, 2, and then the other diagonal, I, 2 minus I. So it'd be 0, 2, 1, 1, and then 2, 0. So it's really only eight different places you have to check for 3 in a row. And here's where the check's actually done. So basically, we go through every single trio in potential wins, and if it is actually a win, then it will in fact be only one item long. And if it's for X, then we know X wins. If it's for O, we know O wins. And this will assume that it's getting a legal position, not a position that's invalid. Because, for example, obviously, if you were to pass in a position where X has 3 in a row and O has 3 in a row, that's impossible. But this will just return whichever one it finds first. And if it doesn't find any, then it just returns a draw. And by draw, that is a draw from the perspective of the static eval. It hasn't found a win, so from its perspective, it's a draw. But in terms of the dynamic evaluation, it could obviously be something other than a draw. We just don't know yet. So that's it for the helper functions. Now we basically get into the main function here, which is solve. And this is going to basically take in a position and return back to the user whatever the evaluation is. So the very first thing we do is we check the static eval. As you can imagine, because if it has a static eval that's decisive, then we don't have to do any branching. So if it's not a draw, then we know it's decisive, and we just return whatever the static eval gave us back, which is something like X wins or O wins. But if it is a draw, then we continue on. The return cuts the function, so if we hit this, it doesn't continue going. But if it is a draw, we do. So here, we're going to check to see, is the position full? Because if it is full, then we can know for sure that it is a draw. Because if there's no spaces left to go and there's no 3 in a row, it has to evaluate as a draw. And otherwise, we continue. So here we recognize there is no 3 in a row. There are spaces left, so that means we are going to have to do some branching. So the first step in doing that is checking to see whose turn is it. That's important. And then next, we're going to get the branches. So we're going to pass in the position and whoever's turn it is, and we're going to get back a list of all the positions that could result from that player making a move. So it's going to fill in one symbol for each blank space and return a copy of that. And then this is basically the main line of the entire program, where we're going to be using recursion to get the evaluation of all of the positions. So we're calling solve from solve. We're passing this function into itself. And what that's doing is it's basically just relying on the fact that we know we're going to eventually hit a base case. This isn't going to run forever because we know we're either going to get 3 in a row or we're going to run out of spaces. So we can safely do this. We can safely generate this list of evaluations that pair to each of these branches by calling the same function, and we don't have to worry about something like a Stack Overflow. So once we get these evaluations, we are then going to check to see, based on whichever player it is, and then playing as best as possible, how the position is actually going to evaluate. So if it's X's turn, X obviously would prefer to win, and if they can't win, they prefer to draw. And if they can't draw, then they have no choice but to lose. So that's exactly what it does. It checks to see if X winning is in any of the evaluations. It doesn't matter if it's one of them or all of them. If it's any of them, X will choose to win, and therefore X wins. And else if X can't win, that means it doesn't exist anywhere in the evaluations. X would like to draw if drawing is at all possible. So it checks to see if draw is in the evaluations. And then finally, if there are no wins or no draws for X, X has to lose and O wins. And here in the else, you can see we have the exact same thing for O's options. O would like to win if at all possible. If there are no O win possibilities, O will draw, assuming there are draws. And if there are no wins and there are no draws, O has to admit that this position is winning for X, and that evaluation will be returned. So this is essentially how the whole program works. It's a little less than 100 lines, not too bad, but it's pretty simple, and it will build out the full minimax tree under any position that's passed into it. So let's go ahead and check out some of these test positions, and we will plug them into our program and see how they work. So let's import main, and we'll also import positions, and let's test one of these. So we will do main.solve of positions dot, let's do x move 1. So this is going to pass in this first 3x3 list here, where x just makes a single move in the corner, and we will find out how this evaluates. And as you could probably guess, it's a draw. So, there's nothing, there's nothing exciting going on there. Neither side can force a win. Let's test X's second possibility, where they go towards the top. And that's also a draw. and X's only third option is going in the center, which is also a draw. So there's nothing that X can do to force a win from the starting position. The starting position is a draw. But there are some other sort of exciting positions here we can take a look at. So for example, here's a case where X wins. If X goes in the corner and then O goes directly next to X, this is X win 1. You can see X wins here. O can't stop it. Same thing for here. If X goes in the corner and O also goes in the corner, that's a win for X, and here as well, if O were to go to the side. So there's a bunch here. If you want to go into the GitHub repository and test some of these out, you can do that if you want. But for now, there's no reason to go through all of these. I think this is enough to explain all the code. So my goals for the program were to write simple code and follow Minimax strictly, and of course the result of that is going to be a ton of extra work and slow performance. You might have noticed that I didn't even test the opening position to tic-tac-toe, just because it would have taken about 15 seconds to solve, which obviously is very slow. So if we wanted to step away from those goals and try to write fast code, what we would find is there's 3 really easy improvements we could have made. The first of which is storing every position globally, so we don't have to resolve the same positions over and over. The second we already talked about, which is checking for symmetry. If a position can rotate or flip to a different position, it'll have the exact same evaluation. And the third one is that we should be evaluating every branch one at a time, instead of generating all of them and then checking them. So for example, if we had a position where it's X's turn, and the very first branch evaluates as winning for X, we don't even have to check the rest of them. But in the current program we are. We're generating all of them, and then we're evaluating. So that's it for the video. If you enjoyed it, don't forget to like, comment, and share. Tic-tac-toe is obviously a very simple game, but in the future I'll be making videos on much more complicated games. So if that's the kind of thing you want to see, don't forget to subscribe, and thanks again for watching.